Start the recording and begin the lecture. So, okay, welcome to the last lecture of the course. The topic is going to be some advanced topics, and it is going to be quite short. It's only 13 slides, but it is quite condensed. And the overall idea was simply to include some of the stuff that didn't really fit anywhere else. And most of these things are slightly more advanced, but they are still something that everyone who is doing good at programming should be at least aware of. So this is just maybe a 20-25 minutes lecture on these topics, and then I have a set of handstones for you. So small recap on the streams. You remember that during the first lecture I showed you that when you're launching the kernel, there is going to be the kernel name and then the brackets where you specify the number of thread blocks and the number of threads in each blocks. And what happens here is that the kernel is based to a stream that acts like a queue from which the device will then pick up the kernels to be executed at some point in some point in time. And by default, what happens here is that all the kernels go to so-called null stream or stream number 0. So that is a stream that is created automatically by the CUDA runtime system. And if you don't specify the stream anyway, then everything goes to the null stream. The operations in the stream in general are executed in order, and this means that the kernels are executed in order they are issued, and only one kernel can be active at any given time. And this allows you to synchronize the execution by dividing the computation into several independent kernels. And blocking operations such as a CUDA memcopy will wait until the null stream is empty. And this means that kernels and memory transfers cannot overlap. And the key thing is there that these blocking operations, they wait until the null streams is empty. There is no talk about any other streams yet. Of course, in CUDA program, you can create several streams. And what this allows you to do is that you can actually insert kernels to 2 different streams, and then the device can actually pull kernels from both of these streams simultaneously. And you can, of course, then also have a different kind of transfers also happening. But this is something that I will cover within 1 or 2 slides. And the way you handle streams is that you have an object called CUDA stream T. That you have an object that is type of CUDA stream T. And you use the CUDA stream create to create the stream, and you use the CUDA stream destroy to destroy your stream. So you create one and you destroy it. And as already mentioned, the null stream is already created at the beginning. You don't have to care about that. And earlier, when we had this function called CUDA device synchronize, that will synchronize the null stream. But if you have created a stream yourself, then there is a corresponding function called CUDA stream synchronize, and you give it that stream to it. And this causes the host thread to wait until that stream becomes empty. So whatever kernels and memory transfers you have put this new stream, the host will wait until they have all finished. Many familiar CUDA functions also have asynchronous variants. And this means that the asynchronous variance basically behaves in the same way as a kernel. So the request to do, for example, a memory transfer is simply placed into the stream. And then the main thread will simply return immediately. So there is and you know which function is asynchronous by this async postfix that is added to the function. So we have CUDA memcopy async here, which is otherwise identical. There's destination source, the number of bytes we are moving, and the direction of the transfer. But then we also specify the stream. And we also have CUDA memcopy 2D. We have an asynchronous version of it. And then there are functions such as CUDA memset, CUDA memset 2D, and CUDA memprefetch async. And this is something, this asynchronous CUDA prefetching is something that I will return in the very end of this presentation. And the key thing to note here is that in all streams, if you don't, in all these functions, if you don't specify the stream, it is going to affect the null stream. So you can actually use these asynchronous functions even when you haven't created a stream explicitly, because it will default to the null stream, and that means that you will place a request to do, let's say, a memory transfer into a stream in the same way you are replacing request to execute a kernel at some point in the future. And of course, then you also want to place these different kernels in different streams. And it happens by that you give this, inside these brackets, you give this fourth argument called stream. So the arguments are the number of blocks, the number of threads in each block, the amount of shared memory that is to be allocated, and the last one is the stream to which you want to place this kernel. There is a couple of things to mention about the null stream, because in addition to being a stream that is created automatically, it has some special properties that you should be aware of when you're making an application that uses several streams. And the one thing is that other streams you create cannot run in parallel with the null stream. And the other streams synchronize implicitly with the null stream. So if you have created several streams and you have put kernels and asynchronous memory transfers to all of them, and then you called CUDA device synchronize, that will actually force the host to wait until all streams are empty. So this can lead to situations where you actually limit the parallelism if you are simultaneously issuing kernels and memory transfers to the other streams while you are still doing stuff with the null stream. So in general, if you want to use multiple streams, you should do all work on those new streams and leave the null stream alone until you actually want to synchronize everything. And there's also pointed out that the synchronous, when you use this synchronous or blocking memory commands such as main copy, this will force other streams to also synchronize. So when you move to using streams, you should then go and actually use asynchronous data transfer commands and specify the stream in which you want it to be placed. And just one thing that you can change this behavior when you create a stream, there you can give it a flag, and there's this flag called CUDA stream non-blocking, and this will actually change the behavior in such a way that the stream you have created will operate independently from the null stream. Then there is a very important topic to cover, which is called a page-locked host memory. And in general, in the modern GPUs, the GPU and the CPU host, they share a common address page. So earlier in older versions of CUDA, you sometimes had to convert between addresses that were actually in the host memory and that were in the global memory. By the modern GPUs, it is actually the same address space. But by default, the host cannot go and access the global memory directly, or vice versa. And if you want to create a situation where the host, where the device can access host memory, then you have to allocate a page-locked memory. And there are two main variants for allocating it. First one is called CUDA malloc host, and the second one is called CUDA host malloc. And there was some type of historical reason why they had two of these. One of these was created first, and then they realized that sometimes you have to pass on different kind of flags to this call, and that's why they added this CUDA host alloc. And then there is also, if you allocate memory using either one of these functions, you must free the memory with CUDA free host. And if you have already allocated a buffer of memory using, let's say, malloc, do we have questions somewhere?
Is one of them deprecated?
I checked the documentation just before the course, and I had this memory that one of these was deprecated, but I could no longer find it. But definitely this one that takes the flags, that is probably the one that will stay in the future. That would be my guess. But last time I checked the CUDA documentation, I couldn't find any mention of one of them being deprecated. Okay. So what these functions do is that when they allocate the memory, they will actually tell the operating system that this memory page must be, the memory pages to which this allocation falls to must be pinned into memory. So the operating system is not allowed to move it anywhere, because otherwise operating system might be allowed to move the memory to a different location, and to the virtual addressing, the application is not going to notice it. But the GPU, because it's communicating through the PCIe, that will notice if the data has been moved somewhere else. So basically this page-locked memory means that memory is guaranteed to stay in the same physical location in memory. And in that way, the GPU can actually access it through the PCIe connection without any kind of safety issues. So these were three functions that you can do when you just want to go and directly allocate a page-locked memory buffer. But if you have already allocated memory, you can turn that allocation into a page-locked one by calling CUDA host register, and then you can remove this pinning by calling CUDA host unregister. And regarding these flags that is accept, for the first one, you can in most cases give a CUDA host alloc default. That based on the documentation will basically cause a situation where this function here, this CUDA host alloc, will behave exactly the same way as CUDA malloc host. If you are running with some older version of CUDA, then you have to go and take a closer look at the different kind of flags. But the modern GPU, this CUDA host alloc default gives you exactly what you need in most cases. And when you are doing the registering already allocated memory, then in most cases you want to use CUDA host register default. And that will also cause a situation that is in most cases beneficial, but in most cases exactly what you want. Otherwise, you want to go and check exactly what each flag does, because there are situations where you might have multiple GPUs. And with older versions of CUDA, you had to make sure that if you would move this data between two GPUs, let's say, then you must make sure that you allocate it as a portable memory. But that should no longer be relevant. If you use the default flag, that should give you that would basically give you the behavior that you're expecting by default. And one of the other reasons for using page lock memory, in addition to the fact that GPU cannot access it, is that it can provide you higher memory bandwidth when the GPU is actually accessing it. And now I'm talking about situation where you're using the CUDA memcopy operation. So if you are just moving data from regular memory allocation to GPU, you will get a reasonably low memory bandwidth. But if you have gone and page lock this memory, then you potentially get a higher memory bandwidth. Because in order to do the transfers, the operating system, the driver actually has to go and at least temporarily page locked the area of memory that is currently being transferred. So you avoid if the driver doing this page locking implicitly if you do it explicitly in advance. But still point out that even though page lock memory can be quicker to go and move around, it is still way slower than the global memory of the GPU. So it's only special cases where you want to go and use page lock memory and access directly from the GPU. And if you're using this asynchronous data transfer functions, then definitely it must be that you have page locked the memory that you're using those transfers. In older GPUs, this would actually cause error, so it refused to do the copying. But I checked with the V100s with the cabinet guys, it seems that even if you don't do the page locking, it will still do the transfer, but it's slower. So the best practice is that if you are planning to use asynchronous data transfers, then you should go either allocate page lock memory directly, or you should register the buffer you have allocated earlier. And here is just one example from the earlier lecture where I showed you that we got only 5 GB of memory when we are doing this data movement, and then doing an X operation and then moving it back. But if we first would go and call the CUDA host register and we will register this memory buffer using this CUDA host register default, now we will actually get about 12 GB per second of bandwidth out of this thing. But there is quite a variation on this because this is just a single measurement. But in general, there is a difference in performance if you page lock the memory, even when you use these blocking versions of the data transfer functions. And here I have this example where I have created 2 streams called P1 and P2, and they have been visualized with these 2 bars here. And then I'm going to insert data transfer request to the first stream, and then second data transfer request to the second stream. And you can see that they will actually start now running in parallel on the GPU device side, or actually it's the memory controllers that control the PCIe that is doing the transfer. And then right away, it is actually going to return from these functions because they are non-blocking. And it's going to insert the 2 kernels to the 2 streams. And then it's going to put a request to the stream, both streams, to actually move the data back. And then it's going to call the CUDA stream synchronize for the stream number stream P1. And what's happening now that now the host thread is waiting for the stream P1 to become empty. And at the same time, the device is doing the 2 data transfers. And when the data transfer is ready, it's going to start running the kernel. And then once the kernel is ready, they both are going to start doing the data transfer back to the host memory. So it is all running concurrently and independently for each other. And once this first stream P1 has finished with this last data transfer, this CUDA stream synchronize is going to return with the error code indicating it was successful because the stream is now empty. And then the host is going to call CUDA stream synchronize for P2. And since the P2 is already empty, it is going to return right away with the error code that indicates whether or not the stream was successful or not. Then, if you want to go and monitor and coordinate streams, there is something called events. And event is something that is first created. So you just use a CUDA event create to create the object that is of type CUDA event T. And once you are done with the event, then you call CUDA event destroy to destroy the event. And one key thing to note here is that this CUDA event destroy is safe. So I will be showing you different functions how you can use events. And if you have used the event it's as a function, it is perfectly safe to go and call this destroy function, because it will wait until the event is no longer used and only then free the necessary the resources that were allocated for the event. And the first thing you can do with the event is that you can place an event into a stream using a CUDA event record function. And you have to specify the event you want to place in the stream, and then you want to specify the stream where the event should go. And it is simply once the device reaches the event in the stream, it will basically go and record information into the event. So it doesn't really execute any code. It is simply recording, for example, when the event occurred. And so you can use it to record when a kernel, for example, started. If you place an event into the stream before you place the kernel there, and then you place the second event after the kernel, then those two events that can tell you, for example, when the kernel started executing and when it stopped executing. So that is one of the main functions how you can use events. You can also use events to synchronize. So you can call CUDA event synchronize to make it so that the host thread is going to wait until the event has occurred. So you could, for example, place an event just after a kernel and then call this synchronize function. And that would basically make the host thread wait until that event occurs, and then the host thread is allowed to continue its execution. You can also check if the event has actually occurred already. So there is a CUDA event query, and you give it the event you are interested on. And if the stream has already reached the event, then it will return you CUDA success. But if the stream is still in a process where it hasn't reached the event, then it will return CUDA error not ready. And in this way, the host thread can, for example, see if a particular kernel has finished. Because if you place the event just after the kernel in the stream and then call this query, you can go and check if the kernel has executed. Because after the kernel has finished, it should reach the event. And once it reaches the event, it should start returning CUDA success instead of CUDA error not ready. You can also make a stream to wait another stream that has an event placed into it. So if you have earlier used the CUDA record function, if you earlier used this CUDA event record function and you have placed an event into stream A, and then you take this event that you have placed and you here, and then you take a stream number B and call this function. Then the stream number B is forced to wait until the stream A has reached this event. And in this way, you can make sure that you can actually synchronize two threads without the main thread being involved in any way. And the key thing that you will actually, and one of the key things that I already mentioned there, that you can use events to time how long it takes to execute the kernel. And this is actually something you will end up doing in the first Handstone. And there you take two events that you had created earlier and you have placed them into a stream. Then you will give them to this CUDA event elapsed time function, and it will tell you return in milliseconds the time difference between the two present time when those events occurred. So you do it one event before kernel, one event after the kernel. You wait until the kernel has actually executed, so you have to do some synchronization, and then you call this function to get the difference in time. And you can, from that, you can get a reasonably accurate estimate for how long it took to execute the kernel. Then one of the nice functions with the modern version of CUDA is that the modern GPUs can do something called managed memory. And the easiest way to explain what managed memory is by looking at the example here. So I'm again going back to this AX kernel. But you can see that this is now a bit different because we are taking one pointer called X, and we are allocating the memory using CUDA alloc managed. So we just get the pointer out, and we specify how many bytes of memory we want to allocate. And then the host will go and use the pointer as just like before, it is going to initialize it. And then we are launching a kernel, but the key thing you notice here that we are actually passing the same pointer, the kernel, that we were earlier using the host. And then we are doing synchronizing, and then we call CUDA free to free this pointer. And if you do this code, you will actually see that it runs just as before. So it looks like the host can go and access the memory here. And when you call the kernel can go and actually access the memory right away. And the beautiful thing there is that data, when the GPU is accessing it, is actually going to be automatically loaded to the device memory. And then when you do a synchronize, you wait until the kernel is ready. And after this point, you could actually go and the host could go and access it. And then the data is going to be automatically pulled from the global memory into the host memory, and the host can keep using it. The only thing is that you must call CUDA device synchronize after doing a kernel before the host starts accessing it, because otherwise you might have a situation where both the host and the device are simultaneously accessed. But the actual data movement is done completely transparently from the user. And the way this works is that when you go and allocate memory buffer using CUDA memory managed, and then go and access this memory from either the host or the device, either two events can occur. Either if the corresponding memory page that is going to be on x86 around 4096 bytes already is either in the host memory or the GPU memory, then the memory controller or the cache will simply give the thread the data as before. So there is nothing different there. But if it happens that the data is not at the moment, for example, device memory, because the kernel has started, then the memory controller in GPU will trigger a page fault. So it will realize that this page of memory doesn't exist in the global memory yet. So it will trigger a page fault, and this is going to cause the driver to go and start memory transfer automatically. So it will take this memory page where the address is located, and it will do a synchronous transfer over the PCIe connect to move the data to global memory. And I believe I have a question.
On mute. Does CUDA free X for the host memory as well?
Yes. If you have gone and allocated the memory with the CUDA malloc managed, then you must free it with the CUDA free. Okay. Okay, so we're saying that if the memory is not already in the GPU memory, it is going to trigger a page fault, and that will cause the driver to start automatic asynchronous data transfer that is completely transparent to the application thread. And then the thread will pause until this data transfer has finished and the corresponding memory page has been moved to global memory. And then it allows the thread to continue executing it. And from thread's point of view, nothing happened. It was requesting from the memory controller. It was going to the cache told it that I don't have the data. It went to the passed the cache to the memory controller. And there's a memory controller who did this all transparently. I believe I have a second question.
Are we limited with the GPU memory size?
In this case, no. So could you mute the microphone? Yeah, so in this case, no. So the GPU will basically see the entire memory in the machine. And it will simply then, if you every time you access it, it is going to pull the corresponding memory page from the host memory. What can happen is that once the GPU memory starts filling up, then it has to evict pages and send them back to the host memory. And this can, in some cases, if the memory access pattern is not very good, it can cause a situation where you lose performance. And as I already mentioned here, then fetching this memory in this way, even though it makes things very simple, it can get a bit expensive if you're accessing the memory in a somewhat random pattern, because every time you have to get a byte of memory that you don't have, you have to load the entire memory page. So there is going to be a lot of overfetching occurring. I believe I have another question.
If we use managed memory, is it not possible to measure execution time for only kernel execution, eliminating memory access?
Could you repeat the question?
If we use managed memory, is it not possible to measure execution time for only kernel execution, eliminating memory access?
Yes, so there is a problem if you use managed memory and try to measure the execution time, because at least most profiling tools actually show the data transfer as a part of the execution time for the kernel. So in that sense, things become slightly more complex. So in one case, you launch the same kernel and the data happens to be in the host memory, and it has to pull the data to the PCIe. It will show that the kernel took longer to execute. And in other case, you call it again, but the data happens to be mostly in the global memory, and then the runtime will be slower. And this was actually one of the reasons why I'm talking about this managed memory all in the end of this presentation, because a lot of the things about the stuff I did during this morning would have been really difficult to go and demonstrate. And one extra complication is that at the moment, when you're running some of the profiling tools on a Kebnekaise, you have to go and disable the functionality in the profiler that would actually take the managed memory into account. For some reason, there is going to be error, and you have to do it either with the sudo access, and with some machines, it is going to fail completely. And that is something that you will see in one of the Handstones you do later today.
One more question. Can CUDA device synchronize be made to sync only selected data structures?
I'm not really sure exactly what that question means. By synchronize, I would usually think like CUDA stream synchronize, or can the person who's asking the question clarify what they mean exactly by synchronizing the data? Is it a data structure or data transfer? I'm sorry. Yes. So here I'm seeing that I'm talking about CUDA device synchronize, and this was the command that synchronized every stream that has been created. So is the question that is it possible to make the host wait until a GPU is done with a specific section of the data? Is that the question? Okay. Well, if the question is that, yeah, go ahead. Yes.
Okay. Am I audible?
Yes.
Yeah. So I understood on your page 11 that if you make managed memory, it gets pulled into the device automatically. You manipulate it on the device, and before you want to manipulate it on the host, you have to do a CUDA device synchronize that it is pushed back. I could easily imagine a situation when you have multiple data structure, managed data structures, and these pulling back, I assume, is resource expensive. So I might only want to get one of these data structures on the host to manipulate, and the other data structures I would like to live on the device, and because I will next manipulate them on the device, and there's no reason to push it back to the host.
Okay. Now I think I got the question. So with the modern GPUs since Volta, I believe, in both directions, what the data that is being transferred are only the data memory pages that are being affected. So the only thing that this CUDA device synchronize does is to make sure that the host and the device are not simultaneously trying to access the data. But after you synchronize, no data movement will actually occur on the Volta. It is only when the host starts accessing the data and causing page faults, then it will actually transfer only those pages that is needed. So it's a very granular. If you go to some older generations, pre-Volta, I believe that was happening there, that when you do a page of managed memory, it would actually allocate it from the host global memory. And then when the host would start accessing it, it would page fault for the data that actually needed. And when you launch the kernel, it would move it then kind of back when the GPU needed it. And in the end, it would actually copy the stuff entirely into the host memory. But with Volta and newer, it is done granularly page by page. So the only extra data movement you do is the fact that you move the whole page at once. Otherwise, there is only the data that the host is needing. That is the data that is being sent back. Was that the sufficient answer?
Yeah, but then I might only need okay, I need to think it through. Thanks for the answer.
Yeah, you're welcome. Okay, so that is what managed memory. So the only remaining part is that since the data transfer is being done only when the GPU or the host is actually trying to access something on the memory page, that can be a problematic because then you just kind of starting the data transfer late. But if you already know that certain data is needed on the device in advance, you can call CUDA mem prefetch async to give it the memory address and the size of the data to be prefetched. And then you have also to specify to which device, because you have to, in this point, you don't know which device the data is actually being moved. And this will actually tell the CUDA API that it will start prefetching the data in advance to the GPU memory. So when the kernel will finally start using the data, there is a higher chance that the data has already resides in the global memory. So there is no reason to do page faulting in that case. And now I'm at the end. So I have quite many handstones here. And the reason why 5 of them is that once I had finished with my other materials, I had some excess handstones. And I simply decided to put all of them here in some form. So if you feel like you don't have the time to do all of them, don't feel bad about that. It's I would say that it's about double the amount of work compared to the previous handstones. I just put everything here, so if people are curious, they can still do them if they want. So all the handstones are under the 4 advanced. And the first handstone is called 1 async. And in there, you will learn how you create a stream. And you also learn how you can use asynchronous data transfers. And on top of that, you then also learn that how you can measure the execution time of the kernel using events. And the second handstone is called 2 multi-gem. And here you learn how you use multiple streams concurrently. So I will actually create several streams. 3-point pipeline is an example where you actually use 2 streams to pipeline the computation in such a manner that you can overlap data transfers in one stream with the computation done in the other stream. So it's a very similar handstone to the second one, except that in the first one you will create a stream for every single operation you are doing, and in the second one you have to introduce extra complexity to make it so that you use only 2 streams to do the pipeline. In 4-point managed, you will learn how to use managed memory, which should be reasonably trivial in the sense. So I try to make assignments slightly more complex when actually making you use a couplage through the operation. So you will learn how to use some of the vendor libraries that come with CUDA. And the last one is slightly more complex code where you end up actually modifying a code that computes ALU factorization without pivoting. And this was a handstone that I first was planning to have like the basically consist for the entire handstones for the last session, but it's just ended up growing and growing to be more complex. So I end up simplifying it and just leaving it here in a form where you can basically see a situation where you have to make a decision if something is computed on the GPU and something on the host. And one of these options is significantly faster, and you are meant to use the profiling tool to see that which one of these approaches is actually the better approach. And solutions can be again found under the under solutions / 4-point advanced. And I'm now